Now, after this one, my dear student, we say that moment of inertia along to Z must be equals to the moment of inertia along to C, then equals to half mr square. Now, we are supposed to recall from the symmetry. We say that the moment of inertia along to the x-axis, for being symmetry, it means moment of inertia along to the x-axis is equal to the moment of inertia along to the y-axis. Now, we could conclude by saying that, therefore, if this moment of inertia along to the x-axis and also to the y-axis are similar, now we say that instead of writing ix, iy, we should substitute the place where there is iy equals to ix. Now, we obtain that this ix plus ix is equal to 2ix as we observe, but iz is equal to ic, which is equal to half mr square. Now, the two times the moment of inertia along to the x-axis is equals to a half mr square. This will be our formula. But here, we were supposed to make x as a moment of inertia along to the x as the subject. If we make it as the subject, we could obtain that moment of inertia along to the x-axis is equal to the moment of inertia along to the y-axis equals to the half mr square. Kwa tumegawanya hapa kwa both side. Ukigawanya kwa both side inakuja ni 1 over mr square. But we know that ix is equal to iy. Kumbe ix atakuwa ni sawasawa na iy, atakuwa ni sawasawa na 1 over 4 times mr square. So after this one, now we could conclude that the moment of inertia through any diameter is given by a half 1 over 4 times mr square. Also, let us go and see for Roman 2, where we have been asked how can we obtain the moment of inertia through an axis passing through the center. Even here, we should recall the perpendicular axis theorem. And our perpendicular axis theorem say that a moment of inertia through z-axis is equal to the moment of inertia through x-axis, then we add by the moment of inertia through the y-axis. Now, my dear student, after this one, let us recall again that moment of inertia through the z-axis is equal to the moment of inertia through the center, which is equal to the moment of inertia for the uniform circular disk. Kwa itakuwa ni sasa na half mr square. We should consider again that for a symmetry, the moment of inertia through the x-axis is equal to the moment of inertia through the y-axis, as we try to observe. So after this, let us substitute that. For a symmetry that ix is equal to iy, if it is the same, let us take instead of writing iy, let us substitute equals to ix, and after there we should obtain 2ix is equal to half mr square, and after this one we should divide by 2 both sides. If we divide by 2 both sides, we obtain that moment of inertia through x-axis is equal to the moment of inertia through the y-axis equals to the moment of equals to 1 divided by 4 mr square. So the formula is the same for any diameter and also for any axis. It should involve the moment of inertia along to the x equals to the along to the y, which is equals to 1 over 4 times mr square. So after this one, let us proceed with using the parallel axis. We have been asking to use the parallel axis so as to demonstrate the moment of inertia. So for the parallel axis, it is similar, my dear student. We could say that for the parallel axis, the moment of inertia, we know that the parallel axis say that moment of inertia through any axis of a rigged body is equal to the moment of inertia through the center, then we add by the mass times the square distance, as we tried to see on our past lectures. So our formula said that for the parallel access theorem, I is equal to IC, then we add it by MD square. But we know that here I should represent the I, this represent I of along to the point AB. Kwa huyu atakuwa ni moment of inertia along to the point AB. And also this equals to IC. Instead of writing IC, we could substitute equals to IZ. Kwa hiyo atakuwa ni moment of inertia along to the Z axis. Then we add by mr square by mcd. Lakini kwenye CD hapa, the distance CD here represent the r. Kwa hiyo yule atakuwa ni sawa na r. Therefore, we could say that if we simplify here, we could obtain that moment of inertia along to the AB must be equals to the moment of inertia along to the center, then we add it by mr square. After this one, my dear student, now we were supposed to substitute the moment of inertia through the center for the uniform circular disk ambayo tunaijua kabisa ile ni sawasawa na half mr square. Kwa hiyo tukisha substitute pale, we should obtain that the moment of inertia through the parallel access theorem must be equals to half mr square, then we add it by mr square. If we sum, we should obtain moment of inertia equals. Now let us we want to get to simplify here. If we want to simplify, we are supposed to, because mr it is common for both operations. Now let us factor it out. If we factor out, we should remain inside the bracket equals to half plus 1. Kwa hiyo tutabakiwa na sasa na half m plus 1, then we multiply by mr. Tukisha hadi pale tutapata sasa kumbe the moment of inertia I is equal to 3 over 2 mr square. This could be our formula of obtaining the moment of inertia through any axis for the parallel axis as we try to use. So my dear student, here on Romani 3 here, on Romani 3, this is for Romani B. Let us go and look for Romani 3. For Romani 3 here, it is the same. We could use here the similar one, that moment of inertia for any axis must be equals, we should consider for the figure. Here we tried to consider for the figure 2, for the figure B. And that is why we get that the moment of inertia is equal to 3 divided by 2 mr square. Now for the figure for the figure 3, by considering the parallel access theorem, we could say that moment of inertia through EF must be equals to the IZ, then we add it by mr square. But IZ here are represented by 1 over 4 mr square. Huyu hapa atakuwa ni sasa na 1 over 4 mr square, while this could be equals to mr square. If we sum this one, because we have the common value here as we observe, we have the common value, let us factor it out. Tukisha factor out, tutabakiwa inside the bracket equals to 1 over 4, then we add it by 1 bracket times the mr square. If we simplify, we obtain that the moment of inertia along to EF is equals to 5 divided by 4 mr square. This could be the formula for the figure Roman C of obtaining the moment of inertia by considering the parallel access theorem. So after this one, let us try to see the application of the perpendicular access theorem. How the perpendicular access theory is applicable on our daily life. This is what we are going to observe. So the perpendicular access theory can be used to determine the moment of inertia of a lamina. Kwa hii perpendicular theory inakuwa inatusaidia kuweza kudetermine the moment of inertia of the moment to use it to determine the moment of inertia of a lamina as we try, e.g. we have the sine-planar layer rotating about an axis perpendicular to the plane. Now we are going to see how the sine-planar layer trying to rotate about an axis perpendicular to the plane. It is also use it to determine the moment of inertia of the disk rotating about an axis along the diameter. Kwa hapa tunaenda kuona vitu vingi sana kwamba ni kivipi hii moment of inertia hii perpendicular axis yole inakuwa inatumika kwa lengo la kudetermine the moment of inertia either for the sine planar or for the laminar. Laminar we are talking about the sine planar, and also for the disk trying to rotate perpendicular along to the diameter. So by saying that, my dear student, this is the end of our session here. Now I would like to invite you again for another session. I wish you all the best. Have a nice moment.